Our next speaker is Tao from Alibaba, and he's going to describe X Engine, an optimized storage engine for large-scale e-commerce transaction processing.
Okay, thank you. So, welcoming you to this session. I'm Tao from Alibaba Group. Today, it is my honor to present our latest work on X Engine, an optimized storage engine for large-scale e-commerce processing, transaction processing. So at Alibaba, we are running one of the world's largest e-commerce platforms. And our database team is confronted with two major challenges to support our massive e-commerce platforms. One is the storage cost. So as you probably know that among all the data we are managing at Alibaba, most of them are business critical. They concern with real business transactions in our economy. So the high availability and durability are very important. We must exploit redundancy to guarantee that, and for that we need extra space that takes a lot of money. And we found that only solid-state drives could deliver enough I/O performance for most of the time, so which are also very expensive. So it is our job at the software side to reduce space amplifications to avoid cases like half-filled leaf nodes in some other storage engines. Another big challenge is the performance of e-commerce transactions. So for most of the time, our databases are receiving read-intensive workload because customers, they often browsing our websites for items that looking fancy to them, but very likely they end up deciding to browse even more before they placing any real order. And in such cases, the workload received at database end is mostly read-intensive, and there are, for example, 10 times more selections than in certain updates. However, when our businesses apply extensive marketing operations on the market, which stimulate people to purchase extensively, and the workload shifts dramatically, so there can be only 3 times more selections than in certain updates in our workload. Although this workload is still rate intensive, these threads, these inserts and updates are critical to user experiences and of course the profits of the sellers in Alibaba's e-commerce ecosystem. So we have detailed numbers of the mixture of different queries in our e-commerce workload in ordinary times and in promotion times. So the challenge basically does not stop here. So in the single-stage shopping festival last year, which is the biggest shopping event on Alibaba's e-commerce platform, our database clusters embraced a 122 times sudden spike of transactions in a single second on the start of the festival. And the peak sales transaction per second reaches 491,000, which could be translated to orders of magnitude higher real database transactions. So it is our job to deliver a very high throughput to process this tsunami-like workload, among which many queries are inserts and updates that are unusual to ordinary days workload. So to solve this issue, we start with studying our e-commerce data that we have collected in our databases for years. In this heat map, I show the data temperatures, which are the record access and frequencies of a small sampled data set along the y-axis. Along the x-axis, I show the several tens of hours. Here, the darker the color is, it means the record has a higher record access and frequency. So we can see that some records are constantly hot during this time window, but the majority of the records are very cold. They are seldom accessed at all. The interesting, some records have changing data temperatures, so they probably shift from the cold temperature to hot temperature and shift back to the cold temperature according to some pattern. So these patterns are reflections of our user behaviors online. So it is our job to deliver a system that could guarantee a very high query performance for those hot records, and also to reduce the storage cost for those cold data that are seldomly accessed. So this is when the log structure merge tree coming into our mind. So this data structure is first proposed in 1997. It consists of 2 components, one residing in the main memory where the performance is much higher than accessing the disk, and the other component resides in the disk. So when the new data is coming into this data structure, it is first inserted into the main memory component where memory accesses are very fast. And over time, when this main memory component becomes full, parts of it are merged into the disk component in a rolling merge manner. So during this process, there are read amplifications, because to materialize one piece of data, it needs to be written back to the disk multiple times. So over these years, LSM trees has evolved into a tiered storage with multiple levels. So new data are first inserted into the top level, where they may have overlapping keys. And when this top level becomes full, parts of it are merged into the next level. So this design helps to reduce the read amplifications, space amplifications, and so on to improve the performance of LSM trees. So right now in the market, there are many LSM tree systems, but many of them are used as KV stores. But to solve our problems, we need to make these systems ready for OLTP transactions. So recording a transaction is more complex than simply a key value pair. So to that end, we design X-Engine at Alibaba. So firstly, to handle the records in transactions, we optimize our data structures in the main memory, which are the mem tables, which are the main memory component of an LSM tree. We make it suitable for records with multiple versions and changing data temperatures. So we also incorporate caches in the memory for the hot records. I will introduce the details of this design later. And because we are making this storage engine and OLTP storage engine, we need to log everything first before they are written into the storage for durability. So this means that we are dealing with disk IOs at a very early stage. So we need to manage these disk IOs and very fast memory access so that we can improve the overall write efficiency. We are also including accelerators like the IPGAs to offload the memory-intensive compaction operations. So this is very important for our case because we want to free the CPUs from the burdens of the memory-intensive operations so that we can use them for the processing of more concurrent e-commerce transactions. Okay. So in the main memory, we optimize the mem tables and the caches for querying over hot records. So in many LSM tree systems, a skip list is used for the mem tables because of their very good write performance. But in an OLTP system where records have multiple versions, the hot records often end up being updated frequently. So a record may have more than 1,000 versions in a blink of an eye. And they are often queried after they are inserted into a mem table. So if a query wants to find some specific version of a hot record, it may need to skip over many versions that it does not need to see, which increases the querying overhead. So we apply a very simple trick. We append the latest versions of the records after the bottom of the skip list into a linked list. So in this way, all of those queries will concentrate on the top of the linked list and the bottom of the skip list, and this has increased the query performance over hot records greatly. Regarding of the caches, we have implemented row cache for point queries and block caches for block caches for range queries. And in our cases, we found that because of the data locality in the e-commerce workload, the cache hit rate can be as high as 99% for most of the time, which help us to alleviate one disadvantage of LSM trees, which is their read performance. So we are relying on caches to deliver acceptable read performance for many of the cases. On the write path, it helps us to swallow the tsunami-like workload, among which many queries are concerning with inserting or updating records in our storage. So our philosophy is to make it as asynchronous as possible. We divide the write path into two phases. One is the read-write phase, where threads processing transactions and buffers the changes they want to make in the storage in the transaction buffer. And when this transaction buffer becomes full, its changes are batched into groups and handled to a set of writer threads to process in a multi-stage pipeline. In this pipeline, we first log all the changes and then append them into the mem tables. So, but here in the logging process, because of the data dependencies among the log entries, we can only use one thread for log buffering and log flushing. But for writes in the mem tables, it is basically embarrassingly parallel, so we can increase the maximum numbers of threads for the stages. So in this pipeline, we tune the number of threads for each stage in order to maximize the CPU efficiency and reduce thread idles as much as possible. So in this figure, we show how much we can improve the write performance using our proposed optimizations on write paths compared with a synchronous bottom line. Basically, our biggest speed up is 11 times over the synchronous baseline. And using the same number of threads, we are able to achieve a much higher throughput. And this is important for us to deal with the tsunami problem. So after I introduce a little bit on how we process e-commerce transactions, the storage cost is also a very big issue for our industrial applications. So in the log structure merge tree data structure, the data are naturally organized into tiers. And those records with very cold data temperatures gradually are merged into the deep levels, where we could apply aggressive compression algorithms to save the space. However, due to the compactions algorithms involved in exchanging, there are memory fragmentations at the deepest levels in the storage. So we apply a dedicated compaction to merge records densely to reduce memory fragmentations as much as possible. And we are also proposing a new technique which merges only code records into the deepest level so that we can apply very aggressive compressions on the deepest level because these data are very likely not accessed anymore. And this code merge operation is powered by our machine learning attempts to identify and estimate data temperatures. So in Alibaba's applications, our optimizations has contributed to around 50% space reduction in some database clusters underneath Taobao.com and DingTalk. DingTalk is Alibaba's messenger application, and this application is designed for enterprise usages, so it never deletes user data unless you do it yourself. So the storage requirement for DingTalk is very large, and this optimization on storage cost is very important to make DingTalk competitive. In the paper, we have detailed introductions of many other optimizations that we have applied in XEngine to make it suitable for OLTP e-commerce transactions rather than simply a KV store. Basically, we are optimizing write paths, the read paths, and the space amplifications using whatever techniques that we can apply. So we can refer to the paper for the details. So in this figure, I show the performance comparisons between among InnoDB, RockCB, which is another popular LSM3 storage engine from Facebook, and XEngine. So along these box charts, the most left-hand side one is the ordinary, represents the ordinary workload online where most of the queries are point lookups, and there are a small number of range queries. And in these cases, InnoDB outperforms RockCB and XEngine, outperforms RockCB and XEngine, but XEngine only delivers a little bit more performance variances, but the performance figures are quite similar. And at the most right-hand side one is represents the e-commerce workload during promotions, where a significant amount of the queries inside that are inserts and updates. So in these cases, InnoDB suffers from a very severe performance variances, and XEngine delivers a more stable performance and also a higher throughput. We have details about how these mixtures make sense in our paper. Okay, so in addition to all those work we have done in XEngine, we are dealing with several challenges to make our product ready for both e-commerce workload and customers in the public cloud. Firstly, like many other LSM3 systems, we rely on compactions to keep the LSM3s in shape so that the queries can be finished reasonably fast, and to deal with deleted records to physically remove them. But due to resource contentions, these compactions are often delayed for some reason, And if this happens, there may be some deleted records that are piled up in the storage. And this will increase the overhead for queries because they now have to skip over these records that shall not be there. And this is a big problem for us. So we are trying to schedule the compactions wisely so that this is not a big problem for queries. And also, like many other asymmetry systems, write amplification is very important for performances. But for Alibaba's case, it also matters to our storage cost. Because of the write amplification, we are more relying on the performance of solid-state drives. So it has become an obstacle for us to switch to cheaper storage media like HDDs. And many of our techniques relying on identifying the code records precisely. So we have ongoing projects studying how to estimate and predict the data temperatures precisely given certain workload, let it be e-commerce workload or some other workloads in the cloud. And also we are working on a benchmarking toolkit to see whether specific optimizations on LSM3 works for some specific scenarios. Because in the past, most of the benchmarks available to us are not specific for some of the issues here for LSM3s. So we are working on a new benchmark that could be used to evaluate our ongoing research and studies. Okay, that's all for my talk. You're welcome to meet us in the poster session or at the Alibaba poster. So any questions?
You mentioned temperature of data as being
Yes.
one of the critical things that you've been working on.
Yes.
Can you describe what your techniques are today for figuring that out? Are you doing queries at the higher levels in the LSM tree to figure out whether, as you're doing mergers or something, to figure out what the temperature of the records are?
The data temperatures, we decided the temperatures using two ways right now. Firstly, because we have studied our workload extensively, so we understand some of the patterns that are deciding data temperatures. So for certain records, because we know the logic creating such records, so we can know its data temperature for sure, because probably some records are going to be called after 10 days of their creation. So this is one case. We can use this to predict a lot of data temperatures, but these are specific to the workloads that we have studied. For other cases where the data temperatures do not have a clear pattern, we are trying to apply machine learning techniques, which is our ongoing research. So basically it's about we take some sampling data set and apply some training techniques and to learn the data temperatures. Yes.
You mentioned the tsunami of these promotions. Those are typically predictable. I mean, you know that one's coming. Do you do anything to get your storage structures clean and ready just before one of those is about to hit?
Yes, of course. We have teams dedicated to predict the tsunami every year. And we, of course, we will ready our system for the predict tsunami. So we clear some parts of main memory because we know there are a lot of data coming in. But we also need to predict the hot records because customers are going to query them. So these records better stay in the main memory. So basically there are a lot of estimation and prediction going on. But right now this part involves manual efforts, which are sometimes vulnerable to human errors. And it is our job at the storage engine side to deliver a very high throughput, write throughput as much as possible so that the jobs for others, for my colleagues, could be easier.
Thanks for the talk. My question is, you mentioned that you use hardware acceleration for compaction.
Yes.
So my question is basically since the data set size is huge in a short period of time, so are compactions not IO bound? And then like how does hardware acceleration help in that case?
It basically we operate in two modes. And during online promotions, we are not, because most of the data are just coming in, so for most of them, they are residing in the main memory. And some of them may be flushed into the first level or some RSM tree. So compaction is not a big issue during the promotions when there are huge volume of data coming in. But it is more of a problem in ordinary days or in non-peak hours, where we could offload the compactions to FPGAs.
Let's thank the speaker again.
Okay, thanks. Yeah, let me switch for you. Okay. Play. Okay. Go back.
That's okay.